accessible, and then we're going into attention, or maybe increase the speed.
But still, I was wondering whether anyone was thinking about dropping it into Niagara Falls.
The camera?
Yeah.
Maybe on the barrel.
Hmm?
Maybe on the barrel.
Okay, that's David from inside the barrel.
Imagine that you play some movie that you're going inside the barrel. Just. No, it's not fun.
Update.
What is the limit where I can move?
Definitely this room, not escape.
Till the end of the.
Oh,
Yeah.
okay.
Everything you will say can be used against.
Of course, I use about that. No problem.
Was it always like that in Denmark? During the lecture, most people had their laptops and they were just working and trying to listen to you.
No, I'm not working and I'm making notes.
Yeah, of course.
What kind of notes? Somehow related.
Why is
Matteo
that
lecture?
your face is more blue than usual?
I don't know.
I believe it makes sense.
Okay. So, welcome to the second lecture of the series. Let me just say a couple of things. So, this lecture is a basic introduction, but also with some very recent research directions and results on the skyline operator. And here I removed the word database. So I think that the original title was the skyline database operator. But the problem is that databases are normally considered as one of the most boring topics in computer science. So whenever I'm making talks saying that I'm talking about databases, people just maybe I'm not going to like that. And the thing is that this talk is on a specific operator. So the question would be, what are we doing here? I mean, shouldn't we do something more important than focusing on something very specific inside some very boring topic? That's a good question. I asked that many times to myself. But the thing is that, in fact, this is a very general operator that concerns some kind of activity that we do every day in our life. I could say this is one of the most important things that we do every day. So taking decisions and choosing among different options. So this is like less narrow than it might seem. So basically the skyline operator in databases is an operator that starts from a set of options. These options usually are records inside a relational database, but they can be any kind of pieces of information. And the objective of the operator is to extract the best elements. So we do that all the time, also when computers are not involved. And of course, this operator can be arbitrarily complex, depending on our definition of best. In some cases, it's easy to see what is the best option. In other cases, it's less easy. And the skyline operator was developed to deal with these more complex cases. And these cases are the ones where we have multiple different criteria. So let me start with a simple example concerning something that we do all the time, booking hotels. So this is a very basic operator, no? So everyone, at time we travel, if we are not important and we don't have a secretary doing that for us, we need to go on booking.com. What I usually do, I use a single criterion, that is how cheap the hotel is. And in this case, the task is very simple. I just take all the hotels, the system sorts the hotels by price, and I take the lowest. So that's quite simple, no? So assume that we want to go to Paris, nice city, we want to book a room. Well, I would probably choose this because it's just $43 per day. This is a simple case. Single operator, we just order the results and we choose the first. But of course, the thing is that there are many different criteria that we may want to use. So, for example, we might want to book a hotel that is very close to the city center. So then we want to walk around, we don't want to take taxi, metro. In Paris there are strikes every day, so it's very. So we want to be here. And in this case, we can use as a criterion the distance from the city center, and this would be probably one of the best options, if not the best option. So our hotel is really in the city, in the center. And we would choose that. So this is another easy case. And of course, the problem comes when we want, for example, to have a hotel that is cheap and close to the city center. And you can see that that's difficult because there isn't any clear answer. This is cheap, but it's very far, it's close to the airport. This is close to the city center, but it's quite expensive. So depending on how much we want to weight these different parameters, we might like one, we might like the other, we might like an option that is a compromise, is a little bit farther, but cheaper. And of course, again, we can then have many other different operators, so it's not just two. Maybe we want something that has 3 stars, that has some sauna, or whatever. There is one standard approach to deal with this that everyone knows, and it's called the ranking. So basically, the idea is that if we know how much we can weight each single parameter, we can just take all these values, produce a single summary score, and sort the results using that score. So for example, if we can say that every kilometer is worth $10, we can just translate all these features in dollars and just make an order of the result. This is the traditional approach, but you probably know using this kind of systems that this is not something that people that want to make business do or ask the users to do. Because users don't really want, in many cases, to go there and say, okay, for me 1 kilometer is worth $10, if you're like in the center then becomes $20, or using this curve, or the sauna is like I can pay $10, you know, this is not what people want to do. And even if people are willing to do that, in many cases they don't have any clue on how to do that. So this is a very simple example where people know the context, but in many cases you don't have a clear understanding of the data. So I think of kind of data analysis that we have done, and you have also been involved with, some of you at least, like to analyze the medical data. I mean, what the compromise between some diagnosis and some number of days spent in the hospital and the ward where you've been, it's really difficult to tell. The skyline operator does exactly the same kind of thing. So it gives you a set of options that should be the best ones without asking you to specify any kind of weight. So it's an operator that is nearly parameter free. You go there, you say, I want it to be close to the city center and cheap, and that's it. So this is what we are talking about. And this is just a database version of something that has been known for many years, for more than 1 century, the Pareto efficiency principle. But yeah, that's not so relevant. The thing is that here in this presentation I'm firstly going to introduce the operator to see how it works. And then, and also why it has been liked so much in research in academia. Then I will identify some practical issues, because this is an operator that is very interesting from a theoretical point of view, but when you try to apply it, of course, things don't go like as straightforwardly and easy as you would expect. And then, starting from these problems or issues, I will talk of some research directions. I will give like an overview of the main directions and then focus on maybe one or two of them, giving more details. So that's the plan. So as the first example, I'm going to use basketball players. So I'm trying to use different data sets just to give you an idea that this is not something that we just use for like booking hotels, of course, which would anyway be already like a very good achievement for humankind. But assume that, for example, we want to hire some new basketball players for a team, and we have some features describing them. So like the average number of assists that they have made during the season or their career, and the average number of points. So you can see that this is exactly the same problem as before, just different kinds of data. So records with multiple criteria. And the good thing in this example is that it's simple enough to give also a visual representation. So here we have the number of points, the number of assists. Every record is represented by a spot here. So this would be the red one, Michael Jordan, 30 and 5.3. And so we can have an idea of what we are really selecting here, because the skyline operator has a very easy and clear geometrical interpretation. And the thing that, the first thing that we can notice is that, as in the previous example, so which one would you prefer? Most of you would say this guy here, because he's scoring a lot of points. But if in your team you need something that is good at passing the ball, well, maybe this other guy here that is also quite cool is better, because he does these things better. So someone could choose one, someone could choose the other. The good thing of the skyline operator is that it identifies this kind of records here and removes all the ones that no one would reasonably choose. So it's a kind of filter. And this is based on the concept of domination. So it's true that here, if you put if you prefer this or that parameter, you would get different results. But the point is that if you compare these two layers here, well, you can see that this guy here is better on this, is better on that. So basically, if you want to choose this and you have an option, then instead of this, you say, well, if I really want this, well, I would prefer this. It's just better on all possible parameters I'm interested in. So we say that this record here, this option, dominates this option, and so this can be removed. Meaning, if you want this, well, this is not really necessary. You can have a better option. And you can also notice that, for example, these two cannot really remove each other from the data set, because like this is better at doing like scoring points, this is better in this other skill, so both might be preferred. The skyline operator, based on this notion of dominance, returns basically all the options that are not dominated by any other option. And this is what is sometimes called the Pareto front, meaning it is the most efficient kind of value that we can reach. This operator has had a tremendous success. So, like, it's been introduced in the database area in 2001, so 12 years ago, quite a long time. And there have been hundreds of papers in top conferences, top journals, focused on this operator. Why? Because, it's cool, basically, no? Because, first of all, you can mathematically show that for all reasonable users, where reasonable just means that I'm not going to programmatically choose the worst player. So it's a very reasonable definition of reasonable, let me use this twist, where it selects all the options. So, take yourself, make a choice. If you are not completely unreasonable, the best choice in the database would be returned by the operator. So you will find it in the result. Good thing. And at the same time, well, this could be achieved also if I give you back all the data. You would find the best option there. But the good thing is that this is also the tightest of all possible results. So it means that in the result of the operator, you will never find an option for which there isn't any possible user that would reasonably choose that. So it's very, we can say, found a complete result. This is given the fact that the data has been evaluated only on those parameters, of course. So if you like blonde people, you could also prefer another kind of player, but of course this depends on the parameters that you use. And here you can notice that we didn't specify any kind of weight. We didn't have to say where we like this or that. This is just, we say we are interested in this option, this parameter, this parameter, this parameter, do the computation. So these are the best, the good points, the reasons of the success of this operator. Together with the fact that it's very general. Because get any data set where you have descriptions and parameters, you can just apply it. However, of course, as usual, as we know, theory is like looks better than things are for real. So there are a few practical issues that have been studied recently and still have to be studied. This is also why if you go on Expedia, you don't find any skyline operator there when you book a hotel. You can just sort, decide sorting the result on one column or the other, which in many cases is a problem, by the way, because either you have like really you want the cheapest one, whatever, or typically you have to sort one and then say, yeah, okay, this is cheap, but where is it? No way. So you have to sort for something, you know. So practical issues. Four main, I think that are very relevant and have been studied in the past. First of all, this is complex to compute. Because to decide if I should be kicked out of the result, well, it's enough that there is one single option that is better than me. So I assume that I'm trying to check if I am one of the guys that should be returning the result. I compare myself with everyone else of you except one person. Still, I cannot be sure that I can belong to the result. Because this single element could be better than me and should be like just be preferred. So this is in theory quite complex and the theoretical complexity goes towards like n squared in the worst case. So which in like when the data is large is completely like unacceptable. And the second problem is also related to the size. So this is a fit-and operator, and the objective is that you don't want to like waste your time looking at 1 million records. You want to have 3 options and choose the best one manually. Unfortunately, there are cases when the skyline operator returns just back all the database. Because if you start using many options, or even if the data is distributed in an like unfortunate way, then everything could be fine for someone. And the cardinality of the skyline at the beginning may increase exponentially on the number of parameters of the criteria. So here we start also adding the rebounds. Well, we start having many other records, in particular, like all these might be in the skyline because everyone is not worse than the other according to some specific parameter. So like you can see that now this guy that before we had excluded because of Michael Jordan, well, it takes on average more rebounds, so it could also be a good option and so on. So problem of time to compute it, problem of size. And the third problem is that, of course, in theory in academia we try to study the single operators to understand how they work theoretically, but then in the real world we don't, it's not that the user that has to analyze some data goes there, runs the skyline operator and goes away, of course. Like, data analysis is more complex than that. usually take the data, you explore it, maybe you run the skyline to try to understand how it looks like, then you get an idea, maybe you change your mind on some parameters, you do some kind of clustering, you do many different things. So another problem is what happens when I use this operator together with other things. So I want to find not the best players, but the best teams. That's already a combination of two different options, grouping players together. And finally, there is another problem. Yeah, this will be myself. I took it yesterday in the hotel. This PowerPoint is a very cool feature to remove the background. I didn't know it. It's so the thing is that of course an operator can be very, very cool theoretically, but if users cannot use it or don't want to use it for some reason, I mean it's useless. So I mean very good properties, but then how can this guy really apply this operator to take the choice? So these are the four main issues that I would like to talk about. So basically, in the rest of the presentation, I will just go through them and give some hints about what has been done to address these problems. I cannot really cover everything, of course, so I will be quite fast on the first two, also because these are the ones that have been studied for a longer time. And then I will take maybe a little more time for the other two, and go maybe give also some technical results about those. So, computational complexity. There is one traditional approach that has addressed, that can be used in these cases, and it's something that is very rooted in the database addition. So it consists in applying some multidimensional indexes to speed up the process. And this has been very successful, and in many situations I would say that it solves this problem quite well. So the main idea is that I don't know if you are familiar with R trees or anyway, the idea is that you just take all the data, you put them inside data structure so that you have different records in different nodes, in different sections that are geographically or geometrically organized. And here you can see that the main idea is that if you know that here you have some records, you know that you don't have to go here and check this, for example. Because everything that is here inside this region will be for sure worse than all the records that I have here. So the main idea basically is to take some time at the beginning to give a structure to the data space, to give a structure to the record, and later when I make queries, so that I know that I don't really need to do all those comparisons myself against everyone else. I can just start from here and then maybe go there because here that could be something good, but then I can prune out some options. These kind of approach started immediately. In 2003 and 2005 we had what is now still the reference work for this. Still, when you try to apply this in practice, you can see that this approach is fast, but it's not fast enough, for example, to deal with interactive systems, where a user there, he clicks on a button and you would like to see the result there, doesn't want us to pick. And then something, coming out after a while. And the other problem is that, of course, these indexing structures work when the number of parameters is anyway small. So if you run these and you have 20 parameters that you want to use, it will take some time. So recently we've been working on some other options so that this operator can be used in really interactive system when you want to get the result immediately. And I'm just mentioning two approaches, two directions. So the first one is to use some specialized, well, this is general purpose in fact, but some different hardware. For example, you can take these algorithms and implement them using general purpose graphical processing units, and exploiting the large-scale parallelism that you can have there. You can implement very efficient algorithms there. So this is one option, just use some kind of hardware that can work better, can parallelize. And the second option is more on the algorithmic point of view. This is what we have called anytime skylines or skyline queries. And there the main idea is that to know that the point, record, and option is in the skyline, we have to take a lot of time in general, because we know that there isn't anyone else that is just kicking me out of the result. But it's also true that if I have compared myself with everyone except one, then and I'm still there, the probability that I will still be there at the end is higher than if I just don't know anything about the rest of the data set. So things, in fact, in practice can be less strict than the definition of the operator that just tells you you're in or you're out. So the main idea of these anytime skyline query algorithms is that they start processing the data. Of course, they will not have knowledge of everything at the beginning because they still need time, but at any time they will have an approximate version of the skyline that is maybe not the best one, but is closer and closer to the best results. And the users at any time can interrupt and say, okay, I want the result immediately. Give me what you have. And the algorithm will give you something that is not guaranteed to be the best result, but it's guaranteed to be the best thing that the system could do up with that specific budget in computation, in computing time, for example. So this is another version where you have an approximate skyline that changes in time and becomes closer and closer to the real one, let's say, the final one. And then we have this option, this problem of potentially very big size. Here the main idea that has been used to address this problem, where you get a lot of data and so you can really make no use of it, is that anyway this larger result gives you an idea of what are the best options there. There are just too many, but it gives you an idea of what they are. So there could be a lot of alternatives here in between, but what you can do anyway after you have computed that is to choose some specific number of options that provide a good representation of the whole skyline. This has been called the representative skyline, and the main idea is that first I use the operator as it is, because it gives me some good and theoretically sound result, and then I summarize it. Usually the approach that has been used to summarize this operator, even if there are many variations, but the most typical has been to use a notion of set coverage. So basically trying to find the set of records so that there isn't any record in the result that is too far. So for example, if I return these three records here, this wouldn't be a good representation, of course, of this set, because for example, this is very far from this and is very not well represented. While if I take one record in the middle, maybe one extreme to one side, one extreme to the other side, that gives basically a better representation of the different kinds of records. Not all the options, but the kind of the different kinds of options that you have in the set of best results. So these were the first two problems, where I said I would have just given you a hint and an idea of what are the approaches that have been used. And now, in the rest of the presentation, I'm going to go a little bit more in detail, because otherwise, you just get an idea, but then you don't really have learned anything at the end. So, I will give more details, in particular, first of all, on the issue of taking this operator and combining it with other data management operators, which I think is very important practically. By the way, those of you that have attended my other talk on distances in multiple graphs might have noticed, maybe not, that basically there every different graph, so sorry for those that were not there, but every different graph can be seen as a different kind of option or parameter, and so basically the operator can find an application also there where just graphs are used, are considered as parameters. So it is good to be able to take this and apply, increment it, extend it with other functionality. And now again, as I was saying, I would like to still use examples that are well understood by everyone, but change a little bit, so to give again an idea of generality. So now we looked at, we have data about, taken from IMDb, about film directors and movies. In this specific context, the skyline operator would be something like, give me the best movies that have been directed. Okay? And to do that, I can use like the popularity of the movie, the score, if people have been voting, so information that I can find on the database. And in this case, I could probably find that like The Godfather is in the skyline because it is the one with the higher score. And then I have other results here. And I took many movies that are quite well known. But I mean, this would be an example of the skyline operator. Evaluation and combination of the skyline operator can be a query like that. Find the best directors. Here they are quite different, even if it sounds very similar. No? Find the best movies or find the best directors. But here the main difference is that you can see that like the same director have directed, of course, many movies. And so to make a decision about whether the director is better than another one, you no longer have to check just a score or a parameter value or score, but you have to consider a set of options altogether. So basically you take all the movies directed by Tarantino, and you take all the movies directed by Jackson, and you have to decide which set of movies is better than the other, to understand which is the best director. And these are written in SQL. You can see that puts together like a group by operation and the skyline operator. So how can we do? To understand what are the problems here, we can check some examples. So assume, for example, that you want to compare Tarantino and Wiseau. So these white spots, can you see them from there? Okay, these white spots are the movies directed by Tarantino, and these are the movies directed by Wiseau, according to their popularity and quality. So you can see that this is a very clear example. You can see that every movie directed by Tarantino is strictly better than every movie directed by Wiseau.
Sorry.
I chose this guy because of this photo that is very, like, I think, scary. So gives to the presentation some kind of, dark. And also because this was voted at some point. There was a poll, and he was voted as the worst director ever. So I took a very clear case, and that is real, by the way. It's taken from IMDb. So this movie is called The Room. I will have to see it at some point. I shall. Okay. So in this case, it's quite clear, no? So this guy here is better than that, according to the movies that he has directed. Then we can take some other examples to see that the problem in general is more complex than that. So this is another director called Fleischer. I don't know if I'm pronouncing it correctly. Maybe it's American, so Fleischer. This reminds me of Frankenstein Jr., no? Frankenstein. I don't know if you have seen the movie, maybe not. Anyway, so you can see that again, in general, Tarantino movies are better, but there is one specific movie from this director that is better than some of Tarantino's ones. This movie is Zombieland. Have you seen Zombieland? Anyone? Okay, me neither. I would never see a movie like that with the title, but they tell me that it is indeed need like a very good movie, like some movie that introduce some kind of new genre, where it's like a mixture of horror movie and American teenagers movie, and you know, so it's.
But looking at the title and the stars and the picture, I wouldn't be surprised if it was co-directed by Tarantino.
Yeah. Do you have a question?
I have a question about the x-axis. Is this number of votes?
Yeah. So this is
It's number of votes.
number of votes.
Okay.
Yeah, and this is the number, like let's say quality, so the numerical score. So here, I don't know if you agree, but I would say that.
No, we don't agree.
Okay. Of course, this is the point. You may not agree. So I would say that Tarantino is, in general, is better, but you might not agree, and you should agree on the fact that you might not agree. You cannot do anything like agreeing to that.
One agreement is it. Without the freedom.
So there could be someone saying, I prefer the other guy. That Zombieland is a very good movie. I prefer that. And then there are more and more complicated situations, no? So this is Jackson after the trilogy of the Lord of the Rings. And here now is, I mean, in general, you can still see that Jackson, before doing this, has done a lot of maybe crappy movies. So, but in general, it's very difficult to tell which one is better. So this is so how can we deal with that? One approach that has been proposed is to use a kind of probabilistic approach. It sounds like something, you know, some of those academic tricks, like when you take a problem, you make some mathematical formalization to make it like look like things work. But in this case, it's really like a kind of very natural way of defining the relationship between two groups of records. And the main interpretation here, so the definition, but the interpretation is easier than the definition itself. The interpretation is that I have a set of records here, like a set of movies. I have a set of movies here, and I have to choose how much this is better than that. And the idea is that, well, let's assume that I pick something at random here. Let's assume that I pick something at random here, and then I compare them. And what is the probability that picking anything from here or anything from there, this is better than the other? That probability would be the probability of domination, where domination is exactly the same concept that we saw for the single record case, so that the easy concept. And if you apply this definition to these real examples, you can see how it works. So here, like the probability that Tarantino is better than this would be 1. Because you can see that whatever you pick from here, you pick from there, this would be always better. According, of course, to these two parameters. So we are always using the assumption that these are the two parameters we are interested in. We might use different parameters and get different results. Like, I don't know, scariness of the site. This would be probably, well, I don't know, it would be a hard problem, but still. And the probability that we saw is better than Tarantino is 0. So, here, yeah.
I have a question about this random selection. Does it also respect the quantity, this number of votes? Is among all the votes available or provided?
Which one of the two?
So if you calculate the probability of something,
Yeah.
you respect the quantity of ratings, number of votes.
Okay, so the probability is not, doesn't assume any linearity here. Just checks if the value is higher.
Yeah, that's true, but
Yeah, okay.
the entire set you consider is the set of all votes, or it's the set of movies.
The set that we are considering is a set of movies.
No, so you do not respect the number of votes, actually.
Well,
Just one of the murders.
sorry, maybe I haven't understood the question. So every movie
Yeah.
has a number of votes associated and some score.
Yeah.
And when I compare two movies,
Yeah.
I use both the number of votes and the score. And I say that one is better than the other if it is strictly better on all the parameters. So I say that this is better than this if it has a higher ranking and also it's more popular.
Okay, good.
Yeah, whenever.
What if it is the number of and it is must be matched?
So if we have
If
situations,
something is more popular or worse,
in that case, I have no possibility of saying that that should be removed from the data set, because there might be someone that likes more the one or the other parameter.
so I think that it could be also considered slightly different way. Namely, we can try to pick up not the movies, but to pick up votes. If you pick up one vote
Mhm.
and another vote, the vote for this movie and the vote for another, any two votes,
Yeah.
what is the probability that it is, belongs to these two movies, and if these two votes are better, this one is better than this one.
Okay,
It would precisely respect the quantity.
yeah, so what you're doing here is basically with the same definition. In this case, the set would be a set of votes, not a set of movies, and then you would apply the same definition.
Yeah.
So basically,
Not because you wouldn't respect this number of votes in the comparison. What is better? What is better would be based only in that case, what I'm talking about, only on ratings.
yeah.
Quantity will be
Yeah.
respected
Yeah.
by the
Of course, I mean,
domain.
yeah, we would apply the same definition to a context where the parameters are different and the sets are different. Yeah. Okay. Yeah. I agree with that. So basically, this example here makes an assumption that you are judging according to these two things, and you can, of course, apply the same kind of idea of picking random and comparing using other kind of parameters.
So, but if one of these two parameters is only satisfied, so for example, one movie is ranked better than another one,
Yeah.
but it is with a lower quantity,
Mhm.
the number of votes is lower, so you treat this case as neutral. Yeah? Or not?
Yeah, basically in that case, you cannot use that information to say that one is better than the other.
Yes.
If you're
So what do you say? It is.
It's this third example, so I'm getting there soon. We have some cases here.
No. I mean, the probability, if you take a pair,
Yeah.
two items,
Mhm.
one movie, another movie, this one is better than this one,
Yeah.
but the quantity is in opposite. So you
Yeah.
cannot tell that this is really better than this one. So how do you check this probability? So it is the probability of these two parameters are satisfied, both are better,
Yeah.
and all the other cases are the opposite side.
Exactly.
Yes?
Yeah. And the thing is that so let's go to this example. For example, here you can see that you have both directions. So basically, here you can see that you can tell the probability that one is strictly better than the other. Tarantino is strictly better than this Jackson. You can compute the opposite probability, and the situation that you are talking about is also stored representing this combination, because you can see that the two things do not add to one. So points here.
In between there is the rest.
Yeah, so basically the idea is that you have a 70% probability that this will be better than the other, a 26% probability that this will be better than the other, and the remaining probability that you cannot really make a choice because they are incomparable. So that's also one of the options, which is actually something that can happen, no? Because it's not that all the time we are able to tell that some option is better than the others.
Sorry, the probability of the invert comparison should be sum to 1? Like
No.
any
Because there are some
Yeah.
incomparable.
No, it shouldn't be.
So the number of cases, actually we have 4 cases.
Mhm.
One is better than the other. So 2 parameters are better, and it is the first. T is greater than J.
okay.
2 parameters are worse, that is J is better than T. And all 2 other cases that one of them is better while the other one is worse, and opposite is the rest. So in the case of 2 upper comparison, there were no such cases. Okay?
Yeah, exactly.
There were no such cases.
And
So that's why it's summed to 1. In the bottom, there were some these cases, so that's why it doesn't.
exactly. And what you say contains intrinsically, I think, very important piece of information. So you see that the option in between, in this contains two cases. If you have 3 parameters, it contains an exponentially increasing number of cases. And this is in fact a mathematical confirmation of something that we experience when we make choices for real. And the fact that if we increase the number of parameters, then at some point anything could be acceptable for some users, because you could like that specific case, or that I like this more than the others because I care very much about being a French movie done in the 60s, because I like French movies done in the 60s.
Moreover, you track each of these parameters equally. So each of them has the same influence on the results.
Yeah.
So it could be also assumed that we say the ranking is more important, twice as much as the quantity.
Yeah, of course, this was basically the introduction.
The axis, so you just introduce or you multiply this by 2, let's say, if the weight is twice as important, so it's quite easy.
What you say is the other option. Yeah.
It could be even more complicated. It could be said that some weights are not so simple that you can simply multiply by number, but some combinations are greater than the other combinations. So the reality could be much diverse.
Yeah, exactly. So in
That's
fact,
an assumption.
yeah. In fact, basically, the skyline operator is an alternative to ranking. In the situations, so it's not the thing that you apply all the time if you want to make a choice, but it's something that you apply when, like, deciding on the way in which these weights on the parameters is more complex than the resource that you have. And here, in particular, we're saying that it's not just a matter of multiplying, and in fact, this skyline operator has the property that for any monotone assignment and manipulation of the weights, whatever you can obtain as the best result using some kind of ranking will be captured by this, will be in the result. So even if you have some like parameter that if it is twice as much, then you like it 3 times more. So any kind of nonlinear weighting, that is captured here. So this is why it's, from some point of view, a generalization of ranking, and from some other point of view, this has a potential problem that can give you too many results to be manageable, because it covers so many different options. Unfortunately, we have already treated the problem of size that is too big, so we will get back to that maybe later. So this was the main idea on how to apply this operator that is very well defined on single records to sets of records. And a couple of things that are, I think, interesting is that while for the single skyline operator that we have seen before, everything works very well. So you have all the possible good properties, and before we have seen some of these properties. With this extension that looks like in some way natural, and when applied to real cases gives results that look natural. But if we try to study it according to its properties, mathematical properties, it becomes a mess, more or less. So, as we have started the discussion a little bit, I will just maybe skip this and focus on one that is probably the most important property that, for example, is not satisfied here, among many others. So, if we use this definition to compare groups of records, then we don't have transitivity, for example. What does it mean, this? It means that assume that we are using the traditional skyline operator of single records. If we say that A dominates B and B dominates C, where dominates B means it's strictly better, then we can, of course, conclude that A dominates C. So if I'm better than you, and you are better than him, I'm better than you. Or the other way around, of course. And here you can see, of course, again, the geometrical interpretation. No? This is better than this is better than this, so this must be better than With groups it doesn't work. So I can say that a group of records dominates another one. So it's like 60% more probable that I'm better than you, and it's only 40% more probable that you are better than me. So I'm dominating you, I'm better in general, and then you are dominating some other group, and in general, we cannot conclude that this dominates that. Which I would say is quite unexpected, at least to me. So when out of developing the thing mathematically we got it, it was hard to find, that it was going to find examples where it really worked. So, but unfortunately it can happen. And it can happen with some specific weird distributions like this. So it's quite difficult to see it, for real, no? This is the case where A dominates B more than 50%. Of the movies are better. B dominates C, more than 50% of the combinations of comparison of movies are better, but A doesn't dominate C. And so...
Really? A doesn't dominate C?
Yeah, no. If you start checking all the possible pairs of records, you see that less than 50% of the pairs are better than.
Because of these two reds.
Because of these two reds that are incomparable with all these.
Yeah.
They are not around.
So,
Okay.
yeah. And the problem is, yeah. So it's it's a very tricky.
65.
65. Good.
6 to 5.
6 to 5. Yeah. So 65 would be too much. Why this is not just theoretically interesting? This is extremely important from an optimization point of view, because when we compute algorithms, we compute the skyline. Of course, transitivity is fundamental to prune away options. So assume that I start comparing ourselves. No, I take these two records from the database. I say who's better, and at some point I say you're better than me. Okay. So this means that by transitivity, also all the ones that are worse than myself will be also dominated by you. So I can just remove myself from the database and go on and just check Piotr, etc. And that's fine. If you're not the best option, you will be removed, for example, by him. And it is pruning, of course, because you can see that from now on, I no longer have to compare myself to everyone else. I can just remove. And so transitivity is a basic option. Without transitivity, it means that first I compare myself to you, you say, okay, you are better than me. Still, I have to stay there and to check, because maybe, it's myself that removes Piotr from the result, because I'm a better option, so people will just prefer me instead of him. And that cannot be captured by your relationship. So this is very tricky.
But on the other hand, that's true. So you lose accuracy, you lose some information, that's true. But on the other hand, the probability of this case is rather low, I would say. Probably.
Yes, the thing is that the probability of this case depends on the threshold that I want to use to decide when I'm going to kick some results out of the data set. So when I compare myself and him, I can be 50% better than you, 60% or 100% better than you.
Yeah.
Not necessarily if I'm just 90% better than you, I want to keep you in the data set. So, and depending on when I say, okay, that's enough, go away. Okay, depending on that threshold.
So it means that if you are removing the lower differences, we are losing much more in accuracy later on.
It means that
exactly. I'm not so sure whether this relationship is
it's true. So if you just do things so you remove everything that is strictly better than the others, just those, that's fine. But if you lower the threshold, then you also start removing something that is a little bit worse, but not so much, then you risk the probability of incurring this case increases.
So that's the typical problem of the balance. So we have the opposite directions, either to decrease the threshold, or to decrease the accuracy.
Yeah.
So
but luckily there is a solution. So some weaker version of the transitivity,
Okay.
meaning that only a small number of cases is left when I cannot do the pruning. And the main idea here is that it's true that if I'm better than you, meaning my movies are better than yours and you are better than him, I cannot say that I'm better than him. But I can say that if I'm much better than you and you are better than him, that's enough to guarantee that I'm also better than him. This is a form of weak transitivity that is based on the concept of strong domination. And the good thing is that again we can mathematically formalize the much better than you. And this is the formula. It's not a trivial relationship. And this square root comes, just to give you an idea, from the geometrical interpretation of this skyline operator. And the main idea is that if you have a threshold gamma, saying whenever I'm gamma % better than you, that's enough to kick you out, then you can define this gamma prime or gamma whatever, that is this with respect to gamma is 1 minus square root of 1 minus gamma divided by 2. Of course, there is no clear equation there, you have just to follow the theorem to understand why that happens. And in this case, you can use this value to check when I'm much better than you. And luckily, those two formulas are not very different. In particular, as we were saying before, if I want a 100% domination to kick you out, then you have 1 here, 1 minus 1 is 0, gamma prime is also 1. So basically, transitivity holds. There are no possible cases where I have this. If you lower...
So you introduce the levels of relationships.
Exactly.
So we can go even further and introduce 10 levels.
But
very strong transitive domination, very, very strong domination.
But that's already enough. You know, I mean, that already covers all possible cases. When you have strong domination...
No, but you go down and you have the domination down.
Yeah.
So you go from strong domination to domination only.
Yeah.
If you would like to have strong domination, you need to introduce very strong domination. And you can go down from very strong domination to strong domination and from strong domination to domination.
Yeah, but what you are saying is not alternative relationships. It's just alternative values of gamma. So what you are calling like that you want to go to strong domination, it just means that you want a stronger gamma here. So the relationship is always the same. It's not that you have different relationships. The difference is that you say I want to go more and more and more.
A strong domination also a specific case for domination, isn't it?
Yeah. If you say that domination is like 75%, then strong domination, meaning the amount of betterness that you want to have transitivity, is defined in some way. If you say now this I want to be the strong domination, you just take this value, you put it here in the formula, and you get the strong domination of the strong domination. So yeah, you can move back and forth on there, but the relationship is the same. It's not that you have different kinds of strong domination, you have different degrees of domination, and the different degrees are always in this relationship to each other.
The strong domination is also a different kind of domination.
Yeah, it's a different degree, I think. There's a matter of interpretation. So it's not kind of qualitative difference, it's a numerical quantitative difference. Yeah. And if you're interested, I think that in the paper you can also find some, if you like math, the proof of this, I think is interesting as a proof, because basically it reduces domination to matrix multiplication, and then basically uses some property of the matrix multiplication to get back to that value. So probably you're not interested, but if you are interested, also the proof here has some interesting development. And so I think we have already had some kind of discussion, so I would more or less go toward the end now. I will just give you a couple of hints of the last problem, of the fourth that I wanted to deal with, that is the matter of using this measure for real. So having real users, not myself here that I make examples, but a real random user because they are on a laptop and does something using this operator.
So you want to manipulate people?
Sorry?
You want to manipulate people, I said this.
Yeah, exactly. And this is what we have done, in fact, and we have liked that very much. It's nice manipulating people. And the main message here is that, again, you can have a data analysis operator that is very, very cool, that has very good mathematical properties, that you understand very well theoretically or in the possible details, but then just people don't know how to use it, or don't want to use it, or use it in the wrong way, or whatever, and so it becomes useless in some situations. And so maybe it becomes restricted to experts, and normal people cannot do it. That can be, of course, a very big problem. And to understand this, the main idea is that so far I presented many examples where the data looks like that. So points in the geometrical space, two-dimensional or three-dimensional. But usually, I mean, whenever you are you want to book a hotel, this is not what you see, no? When you go online on a booking system, not you see that
For dimensions.
what you see is something like that. So you can see that from theory to practice there is a big difference. So you have some way to some constraints, some maximum price, and you have some facilities, you have lists, so you have visualization, you can order by. There are many possible things that you can do. And one other piece of research that we have been doing recently is how can we take this operator and plug it in there. And so we have developed this hotel booking interface. So this is something that we've done, mimicking, like taking the same kind of interface that you have for real. An example where the users know what they are talking about. So if they fail, it's because they are failing using the operator, not because they don't understand what is the hotel room. And we have, human ignorance is unbounded, of course, but still. And we have used different options. So, for example, we say that the skyline operator is parameterless. That's true, but you have to say that one parameter is one of the parameters you want to use to do the evaluation, for example. No? So it is parameterless in theory, but for real, you have to go there and say, I'm interested in being close to the Colosseum. And you need to, for example, click there. And that theoretically is really useless and not significant at all, for a user can make a big difference. Because another option could be, instead of implicitly asking you to tell me what are your parameters, I just guess them. Whenever you set some maximum values here in the distance, then I can assume that this is not just a constraint, but it's also one of your parameters to compute the skyline. Let me not summarize the results of this, because there is some wine that is waiting for us, and some Italian cheese and sausages that I could use. But I can just tell you in general that it's much, it is good, it is appreciated. It really increases the power of people like booking hotels, so people can do something better, but studying real users, you can see that there are a lot of issues. In many cases, they have no idea whatsoever of what they're doing. So like, for example, they look, they say, I want the number of stars to be high, I want 5-star hotel, and then you ask, okay, this is the result. Why is this in the result? And they say, because it's very close from the Colosseum, for example. Or this kind. So they think that the result has been computed using some other parameter that they have never set, for example. Or they do also things from which you can see that they are not understanding what they're doing. Like they're using the skyline on the price, saying I want a hotel with the lowest price, and then they set the maximum bound, which of course is useless, because if you want the hotel with the shortest price, you just sort of the hotels and you get the one with the shortest price. No need to
But
say,
it means that actually you can justify everything.
yeah,
It's good.
that's good. That's not so good, exactly.
From a commercial point of view, it's very good. So you can find the justification for every result.
Mhm.
It's perfect. The manager would be happy.
I am not sure that that would pass a scientificity test, but still. And just say something else, even that could be interesting. Like, sometimes we make, as computer scientists, we make algorithms that are very advanced, like they use, these probabilistic algorithms that use some kind of random generation or going to give you like some kind of results. Even if they are very cool mathematically, when you use them there and they have some non-deterministic behavior, users might just get completely lost. So like some users start with toggling and untoggling a parameter, like I want it to be cheap, no, I want it to be cheap, no, I want it to be cheap. And every time he does that, using a very advanced stochastic algorithm, he will say, this is the best result. Or now it's there, now it's here, click, clack, clack, these kind of behaviors. Or also non-monotone results, that is also typical for this set coverage approach that I was talking about before. So if I ask you, too far. So imagine that there is a whiteboard here. If I give you 3 points here, 1, 2, 3 records, and I ask you, give me one that is representative, I would give you the central one. If I ask you, give me 2 that represent well, I would probably get this and this, no longer the central one. But if you ask the user and he said, give me the best result, it doesn't like that first you get this. And when you ask the second best, like the first best changes. Of course, there is a paper full of these things that I'm not going to go in detail. So, like this is like a summary. Sorry, it's here. Like this is a summary of references where you can see like these things on representativeness, anytime skylines, computational GPUs, aggregate skylines on groups, or user operations. So here, like you have a range of representation references. But the main point is really that the main message is that even like having a very good operator from a theoretical point of view, and even having an operator that also in practice in some situations proves to be very good, as it did in these tests, there are many things that sometimes are considered as features, good features from us, because they improve the result, the accuracy in general, but they just have the result of completely getting the users lost and confused. And so maybe in practice some other options, some other algorithmic approach could be considered. And I think it's really then time to have, of course, take other questions if you like, and then to get some wine and cheese and things that we will arrange upstairs. Sorry, some wine, some cheese, and some...
after work.
After work at 6 p.m. of course. So thank you for your attention, and if you have, of course, other questions, we can discuss them either here or somewhere.
How many people tested this hobby?
So here we used a think aloud study that is basically kind of preliminary study based on a limited number of people. In our case, it was 6 people. Yeah. And this number, to me, that I have no experience in user studies, seemed not so good at the beginning, because we collaborated with people like with expertise in user studies, because I said we cannot generalize anything. And the main point is that, in fact, we are not at the point where we can or want to generalize. So, if we don't know which one is the best interface for them to access the skyline operator, if we make a user study like based on 100 users where we want to check if like we can compute a quantifiable improvement in like the efficiency in which the time that they take to find a code, or how much they are satisfied. The problem is that the results could be basically scientifically useless, because you would not know if, for example, good or bad results depend on the operator, or on the fact that the interface doesn't allow them to use the operator in a good way. So basically what we do in these cases is like to first make a result, like a kind of study where you have a limited number of people, but a very deep and qualitative analysis. So they are forced to talk, you give them tasks, they compute the task, they take like 1 hour to compute very many different tasks, and they are forced every time that they do something to talk and to explain what they're doing, so that you can get feedback whether they're understanding what they're doing, or whether they have they are finding problems on what they're doing. So this is what the kind of test that we've done so far. And it's called technically a think aloud study. Yeah. And I was quite surprised at the beginning because I was saying, come on, I mean, we will never get this accepted in any database conference. They will say 6. And then we went to CIKM that is luckily, has also some information retrieval component and they're more used with this kind of things, so went better.
No other questions. I hope.
That sounds like a order.
It was an order.
So what should we just take like 10 minutes to go upstairs and prepare the stuff and then have a refreshment?
Yeah.
Okay.
I'm still wondering whether